Welcome back to The Explainer. Today, we're diving straight into the actual ground-level mechanics of gold extraction. We're going to trace the exact chronological journey of ore, from a dusty, solid chunk of rock all the way to a gleaming gold ingot. It's a fascinating mix of heavy mechanics and subtle chemistry, so let's just get right into it. But right off the bat, I want to throw a question your way. How do we actually pull gold out of low-grade rock without pulverizing it into a superfine dust? There's this huge misconception out there that all mining means grinding mountains of stone into absolute powder. Well, as you'll see today, that's not always the case. The real answer is, actually, it's way more elegant than that. The secret sauce here is heap leaching. And if we want to define it simply, heap leaching means slowly percolating a leaching solution right through crushed ore, dissolving the gold, and then collecting that pregnant solution for recovery. Lock that core logic into your brain right now, because that single sentence, that's the foundation for literally everything we're going to cover today. Okay, so here's our roadmap for today's explainer. 1. Demystifying heap leaching. 2. Crushing and heap construction. 3. Spraying and chemical dissolution. 4. Collection and gold recovery. 5. The engineer's perspective. And 6. Greener alternatives. Starting with Section 1, Demystifying heap leaching. Now, before any extraction can even begin, we've got to look at our raw starting material. We are generally dealing with the 5 major types of gold ores, specifically the low-grade, oxidized, or free-milling varieties. Now, because the gold grade in these rocks is so remarkably low, spending an absolute fortune and massive amounts of energy to aggressively process them, it just doesn't make economic sense. We need a method that's efficient, highly scalable, and perfectly tailored to these specific rock types. What I find super interesting here is the stark contrast between heap leaching and the CIP, or carbon in pulp method. I mean, the differences are literal night and day. CIP is this highly complex indoor operation that requires heavy fine grinding and a massive upfront investment. But heap leaching, it's an outdoor process. It relies on a simple coarse crush and minimal infrastructure. It's totally designed to be a low-investment lifesaver for low-grade ores that, honestly, just wouldn't be profitable any other way. Moving on to Section 2, Crushing and Heap Construction. Let's look at the actual engineering mechanics. So here are the first 3 chronological steps of our standard process flow. Step 1 is coarse crushing. We just need to break the raw ore down to a target size of, say, 10 to 50 millimeters. Step 2 is heap construction, which is exactly what it sounds like, piling that crushed rock up safely. And Step 3 is prepping the leaching solution. You have to carefully mix it with an alkali to hit a very specific, highly alkaline pH of 10 to 11. That is absolutely crucial to keep the whole process stable and, more importantly, safe. Okay, I really need to hammer this point home because it's probably the biggest differentiator of the whole operation. Say it with me. Only coarse crushing is required, no fine grinding. Literally, no fine grinding. By entirely skipping that energy-heavy pulverizing phase, mining operators save a tremendous amount of power and spare their machinery from a ton of physical wear and tear. It's a huge win. Once we've got that coarse crush, the ore is stacked up using massive transport vehicles, or stackers. And we're talking huge scale here. These heaps easily reach heights of anywhere from 2 to 10 meters. That's like a 3-story building made of crushed rock. But the absolute most critical piece of engineering in this entire setup, it's right at the bottom. The whole heap is built on an impermeable HDPE liner. This high-density plastic barrier is literally the only thing preventing our chemical solutions from leaking out into the soil and causing a massive environmental disaster. It is non-negotiable. Next up, Section 3, Spraying and Chemical Dissolution. Time for the chemistry. Which brings us right into the final 3 steps of the extraction process. In Step 4, we irrigate the heap, spraying our leaching solution perfectly evenly across the very top. Step 5 is collection. That's where the fluid, which has now traveled all the way through those meters of rock, is gathered at the bottom drainage system. And finally, Step 6 is the actual gold recovery from that collected liquid. But let's zoom in on Step 4 for a second, because honestly, this is where the actual chemical magic happens. As that sprayed solution permeates downward through a 10-meter mountain of rock, it's not aggressively washing dirt away. No, it's a slow, highly deliberate chemical reaction. The core reaction is that the solid gold, Au, forms soluble complexes with the cyanide in the solution. Basically, the gold dissolves right into the liquid. All right, Section 4, Collection and Gold Recovery. Let's get our gold back. So the biggest takeaway of the whole system is right here. Gold is now in solution, no longer in solid ore. This is the ultimate aha moment of heap leaching. We haven't physically chipped the gold out of the rock, we've chemically transitioned it. It went from a solid state, totally trapped inside a rock, to a liquid state just flowing through a drainage pipe. In the industry, we call this fully enriched liquid the pregnant leach solution. But, you can't exactly sell a puddle of liquid to a bank. We need our solid gold back. To get it, that pregnant solution has to go through recovery. The most common methods are activated carbon adsorption, that's your CIP or CIC, or zinc displacement, which is known as the Merrill-Crowe process. Once the gold is chemically yanked back out of the liquid by these materials, it undergoes its final electrolysis and smelting, and boom, that's what gives us those classic, heavy, shiny gold ingots. Section 5, the engineer's perspective. Let's get a little technical. Okay, we need to completely bust a very common misconception right now. Heap leaching is emphatically not, I repeat, not just ore washing. You aren't just out there flushing the gold out directly with a giant hose. Any engineer will tell you this process is a controlled percolation chemical system. It is a highly precise, heavily calculated, and strictly managed fluid flow reaction. And this perfectly illustrates the complex math behind the magic. The efficiency of this entire operation hinges on 3 highly technical variables. Number 1, ore permeability. Basically, how easily can the liquid actually flow through that crushed rock? Number 2, solution distribution uniformity. Are our sprinklers hitting every single inch of that heap completely evenly? And number 3, leaching kinetics. What is the exact speed and energy of the chemical reaction happening down at the microscopic level? It's intense stuff. Finally, Section 6, the future. Greener alternatives. Now, for over a century, this traditional process has relied almost entirely on sodium cyanide. And while it is incredibly effective at dissolving gold, it obviously poses severe toxicity and environmental risks. Just the hazard of storing and transporting cyanide is a massive logistical nightmare. But thankfully, modern chemistry is stepping up. Enter a relatively new, eco-friendly alternative reagent called jinshan. But the real question is, does an eco-friendly alternative actually work in the real world? Well, the data from the Jiajidan mine tells a pretty compelling story. When they used traditional, highly toxic sodium cyanide, they saw an 88.7% gold recovery rate. Not bad. But when they tested the jinshan reagent at a dose of just 300 grams per ton, the recovery rate hit 89.8%. I mean, the numbers speak for themselves. This modern, environmentally safe alternative doesn't just match the old toxic methods, it actually slightly outperforms them. So how exactly is that possible? The secret lies in its chemical structure. Jinshan relies on a core component called carbonated cyanuric acid sodium. Through some really clever chemistry, the cyanide groups are locked up tightly with covalent bonds. Because of spatial hindrance, they simply don't release those free, toxic cyanide ions into the surrounding solution. But they somehow still manage to perfectly complex and dissolve the gold. It's a total game changer. You get all the leaching efficiency, but without the lethal toxicity. Which leaves us with a pretty fascinating thought to end on today. With green chemistry like this now proving it's entirely capable of nearly 90% gold recovery, while drastically lowering the environmental and safety risks, how quickly will the global mining industry abandon toxic cyanide forever? It's a massive, monumental shift in a century-old practice, and we're literally watching it happen right now. Thanks so much for joining me on this explainer, and remember to keep questioning how the world around you actually works.